Assalamu alaikum. Welcome to the next lecture. Today we will discuss about the classification of the transmission line. In the previous class we discussed about the general introduction of the performance of the transmission line, and in that lecture we saw that the performance means calculating the efficiency and voltage regulation of the transmission line. So before going into that, we'll first classify based on certain criteria the transmission line, and on those classifications we may have certain assumptions, and then based on those assumptions we can calculate the voltage regulation and this efficiency of the transmission line. So let us start with the classification of transmission line. Basically, these transmission lines are classified on the basis of three criteria. The first is the length of the transmission line, the second is the operating voltage, and the third one is the effect of capacitance. It is the shunt capacitance. Actually they are quite related or directly related to each other. We can say that, you can see it from here. The first I have just made the table so that it includes all the three parameters and it becomes quite easy for you to understand. The first transmission line is a short transmission line whose length is from 0 to 80 km. We consider it to be a short transmission line, and its operating voltage is up to 66 kV. It can be 11 kV, can be 33 kV, 66 kV, or below that. That is the LT1. And the effect of the shunt capacitance is neglected. When you analyze such transmission lines, we omit the capacitance because we know that the capacitance goes on increasing and the length is increases. Here, since the length is very small, we can neglect the capacitance. After that, we have the medium transmission line whose length is 80 to 250 kilometers, and the operating voltage is up to 220, that is 66 to 220 kV. And in this case, capacitance is considered to be lumped. Lumped means we assume that capacitance, we add all the capacitance of the transmission line and put it at one place. So that is what is meant by the lumped. The third one is the long transmission line. So in first two, we are using the approximations. You can see the approximation here is the capacitance is lumped, sorry, neglected. Here all the parameters including capacitance are lumped. Here this is also known as the exact analysis of the transmission line, because here we use this capacitance and other parameters to be distributed and exactly is exactly the case with the transmission line because all the parameters are actually distributed. The length of the transmission line will be considered greater than 250 kilometers, and operating voltage is greater than 220 kilovolt, that is 400 and above. So you can see they are all the three parameters which I have discussed over here, they are related to each other. Length, more operating voltage, more capacitance. You can see this is also connected to the same. Now coming to the short transmission line, before we have another assumptions. The effect of C for short transmission line is neglected as it is very small, because the length of the transmission line is very small. And as far as G is concerned, that is the shunt conductor, it is altogether neglected for all practical purposes. I have told you in the class as well, because this is not, its value is not so much, so it is better to neglect it rather to make the calculations very rigorous. Now let us come to the short transmission line. We'll first model the transmission line as a two-port network shown below. The output parameters will be the receiving end current and the receiving end voltage. This is the receiving end, and the input side we have the sending end voltage and sending end current. So the above network can be represented by the ABCD parameters. I have perhaps told you that why do we only use the ABCD parameter, because of its obvious advantage, because most of the equipment of the transmission line or the power system are connected in cascade, and ABCD parameters will be multiplied of the cascade system. So here actually we don't, when we finally combine the whole system, we don't calculate the total ABCD parameters altogether. We calculate the ABCD parameters of the individual equipment and then multiply them to get the ABCD parameters of the whole system. For the time being, let us say this when we represent this system in terms of ABCD parameters, so Vs will be equal to A times Vr plus B times Ir. This is actually a general formation of ABCD parameters, and Is is equal to C times Vr plus D times Ir. So here this source and voltage is related in terms of A and B, in terms of the receiving end voltage and receiving end current. Similarly, the source current are related to receiving end voltage and receiving end current by the constant is C and D. In matrix form, we can write it as Vs Is is equal to A, B, C, D, Vr, Ir, because when you multiply this to this vector, you will get again this AVr plus VIR, and then Is is equal to CVr plus DIR. So it is matrix form. For short transmission line, C is neglected and G is taken to be equal to 0 always. The transmission line will be model without the parallel branch, because I have shown you the transmission line model: series resistance, series inductance, and then a parallel branch of shunt conductance and shunt capacitance. But for practical purposes, short transmission line, C is neglected and G is also neglected. So our short transmission line will reduce to this. This is the equivalent circuit of our short transmission line. So writing the KVL in the network, we get here Vs is equal to Vr plus this voltage drop across this impedance R plus Jx. So Vs will be equal to Vr plus Ir into Z. All of them are in phasors. So Z is equal to R plus Jx. Writing KCL at this point or at this point here, it is very one and the same thing, because they share the same node. So Is will be equal to Ir, because there is no other path of this current to flow. So whatever be the receiving end current, same will be the sending end current. So I will compare the equation 3 and 4 with the equation this 1 and 2. You can see Vs is equal to AVr plus VIR, but here Vs is equal to Vr plus IR into Z. It means A here is equal to 1 and B here is equal to Z. Similarly, Is is equal to IR. So comparing this equation to equation 2, Is is equal to IR, that means C is equal to, there is no part of this, that means C is equal to 0, and Is is equal to IR, D is equal to 1. So the ABCD parameters of the short transmission line can be put like this: A is equal to 1, B is equal to Z, C is equal to 0, and D is equal to 1. So writing in the matrix form, Vs, Is, this is 1, this is Z, this is 0, this is 1, VR and IR, like this: A is equal to 1, B is equal to Z, C is equal to 0, and D is equal to 1. This becomes the system. This matrix, ABCD matrix, is known as a, is also known as system matrix. So the two important properties of the two-port network is the symmetry and reciprocity. We want that our system should follow both reciprocity and symmetry. So we want that our ABCD parameters should be such that, so that our system should be reciprocal and it has the symmetry. When it has a symmetry, it means by connecting it on this side or on this side, the voltage current relationship does not change. So it becomes very convenient for us. We don't have to look for the sides, which side to connect to the which side. So in that case, it is very convenient. Same is the case with the reciprocity. So in that case, we need to find out whether this is symmetric or reciprocal. For ABCD parameters, for a system to be symmetric, A is equal to D, and for a system to be reciprocal, AD minus BC should be equal to 1. So we need to check it. Since we have calculated ABCD parameters of the short transmission line, we need to check it whether it follows the symmetry and reciprocity. So you can see here, since we know that from here, you can see A is equal to 1 and D is equal to 1. So that means it is symmetric. Since A is equal to D is equal to 1, that means our short transmission line is symmetric. So for reciprocity, AD minus BC should be equal to 0. A is equal to 1 multiplied by B, D is equal to 1 minus B is equal to Z, and C is equal to 0. It comes out to be equal to 1. So that means our short transmission line is symmetric as well as reciprocal. It is added advantage, because after this we don't have to look for the sides, which side to be connected to which side. So you can arbitrarily connect any side. This can be made to receiving end and this can be made to sending end, or this can be made to receiving end, or this can be made to sending end. That is what I mean by the symmetry. Now coming to the voltage regulation. So we'll first discuss the voltage regulation of the short transmission line. So for voltage regulation, I will use the first equation, that is Vs is equal to AVR plus VIR. So the general definition of the voltage regulation is VR receiving end at no load minus receiving end at full load divided by the receiving end at full load multiplied by 100. From equation this first, the no load VR can be found by putting IR is equal to 0. When IR is equal to 0, this equation becomes Vs is equal to AVR, but VR at this point will be called as no load receiving end voltage, and I will label it as no load receiving end voltage VRNL. So the magnitude of VRNL, because this is the voltage regulation, is always defined in terms of magnitude of the voltages. So the magnitude of the VR no load will be equal to magnitude of Vs divided by the A parameter. A may also be a complex number, so we are only interested to find out the value of the magnitude of the A. So then voltage regulation will be equal to Vs divided by magnitude of A minus VR full load divided by VR full load into 100, multiplying A throughout the numerator and denominator, so it will be equal to Vs minus AVR divided by AVR. From the above, from the last slide, we have already calculated the value of A. The value of A was equal to be 1. So this can be equal to Vs, that is source and voltage, minus VR divided by VR, but VR should be the full load voltage. Now voltage regulation from the phasor diagram. We can calculate the voltage regulation from the phasor diagram. This you have already done exactly the same procedure you have done for the transformers. So we'll do the same analysis for the transmission line. Let us say this is our transmission line. This is the series inductance, this is the series resistance, this is IR, VR, and this is VS. So when we made the phasor diagram, it will be like this. This is VR, and we assume that IR is lagging to this by an angle theta. Now this Vs will be equal to VR plus IR into R plus IR into JX. So we'll first add a phasor of IR into R to this VR. It will be in phase with this. So this and this will be in phase. So that's why it has been shown like this. So this will be IR into R. That is the voltage drop across resistance R. Similarly, this voltage drop is the IR into X, J IR into X. It will be leading to this voltage drop by 90 degrees because it is multiplying J, or in polar form it means it is giving a shift of 90 degree to this phasor. So that means this will be leading to this phasor by 90 degree, and magnitude will be equal to IR into X. So by adding this VR, IR into R, and this IR into X, so this tip and this tip will give, when you join them, it will give you VS. So this is the phasor diagram. So I have simplified over here. You can see again this is IR is equal to IS because they are in series. This is theta, this is delta. I'll let you know just a bit later what is this delta. So this is VR, the same voltage phasor. This is IR into R, the same voltage phasor across resistance R. This is IR into X. This is a voltage phasor across this reactance X. So I have extended this line, this VR, up to, let us say, up to point R, and I have drawn a perpendicular from this point to this point P. So since this is theta, this voltage vector across R will be parallel to this voltage vector. That means this will be theta, this will also be theta. When this is theta, this will be 90 minus theta because this vector, this voltage phasor will be perpendicular to this voltage phasor. This will be 90 degree, and this angle will be 90 minus theta. So this angle will also be equal to 90 minus theta in this triangle OBQ because they are vertically opposed angles. And when this is 90 minus theta, this angle is 90 degree. This will be again theta. So keeping these things in mind, you can see that this OP will be equal to the cos component of this voltage phasor. Similarly, this PR, which is equal to this length, it will be equal to sine component of this phasor. That means this OP is equal to IR into R cos of theta, IR into R cos of theta. I just deliberately put a small r just to not make you confused to this capital R. Similarly, since this value is the sine component of this, it will be equal to PR. This PR will be equal to this length. It will be equal to IR into X, because this is IR into X sine of theta. So with these things in mind, for small value of delta, this is delta. If the delta will be very small, you can see that this B and R will coincide. They will be very close to each other. We can say that this AB will be equal to AR. This AB will be equal to AR. So this delta is actually known as load angle or power angle. So it will be equal, AB is equal to AR. So AB is equal to AR, but AR is equal to AO plus OP plus PR. AO plus OP plus PR from this figure. So AO is equal to VR. You can see AO is equal to magnitude of VR. OP is equal to IR, R cos of theta, IR, R cos of theta, and PR is equal to IR x sine of theta. This is equation 2. From here we can get Vs minus Vr will be equal to IR into R cos of theta plus IR into x sine of theta. So voltage regulation, as we have calculated earlier, it is equal to Vs minus Vr into A divided by A into Vr, and for short transmission line A is equal to 1. So voltage regulation will be equal to Vs minus Vr divided by Vr. So putting Vs minus Vr will be now this Vs minus Vr will be equal to IR R cos of theta plus IR x sine of theta. That is what I have written over here. So the numerator will be IR R cos of theta plus IR x sine of theta. Vr is as it is. So taking IR outside, so this will be equal to R cos of theta plus x sine of theta divided by Vr. So this is the voltage regulation for lagging load, but please try to make sure that this is only valid when delta is very small, because we are assuming this AB equal to AR. So this will be valid only when delta is very small. And this relation we have calculated for lagging load, and when the load is lagging, you can see there is nothing which can make this negative. So this voltage regulation will always be positive. So voltage regulation will be positive when the load is lagging. Now coming to the leading load, this is the leading power factor. Let us try to zoom a bit. Here this is VR. Now we are assuming that the current is leading to this VR. So this is IR into R, that is voltage phasor in phase with this IR, and IR into X, that is leading to this by 90 degrees. You can see this voltage phasor is leading to this by 90 degrees because of the G of X. So this is Vs. This is then Vs. So I have again written this down again so that it becomes easy for you. This is theta. Since this is parallel to this, this is again theta. This, because I have extended it up to this, and then again I have drawn a perpendicular from B to O and a perpendicular from B to R to this line. Let's say this is a QR line, and this is theta. This angle will be 90. This will be 90 minus theta. This angle will again be equal to 90 minus theta, and this angle will be theta. And I have perhaps shown this is theta. Wait a minute. Okay, yes. So this is theta. This is 90 minus theta. This is 90. This is again theta. Because this angle plus this angle plus this angle will be equal to 180 degree. This is 90 minus theta plus some angle is equal to 180 degree. You can calculate this will be equal to again theta. So here these two will not be equal to vertically opposite angles. Now coming to this, again we are assuming that this delta to be very small. When delta is very small, this B will try to coincide with O, and that is the case. This AB will be approximately equal to EO. AB will be equal to approximately equal to EO. We can assume this AB is equal to AP, that is this AP plus PQ plus PQ, AP plus PQ minus this distance. So I'm adding some distance and subtracting more distance to get this. So I am starting from a distance which is more than this O, and then adding some more distance. It gets it is increased to this by this much, and then I am decreasing the whole length from this point to this one. So this AB is equal to AO is equal to AP plus OP minus AP plus PQ minus OQ. OQ, it has to be minus. So here again PQ, this is PQ. PQ is the cos component of this phasor, that is IR into R cos of theta, and OQ. OK is this, that is OK will be same as BR. It will be the sine component of this. Sine component of this will be equal to IRX into sine of theta. So putting in this, you will get Vs is equal to VR plus IR R cos of theta minus IR x sine of theta. So from here, the voltage regulation Vs minus VR divided by VR. So it will be equal to Vs minus VR will be only this term, IR into R cos of theta minus x sine of theta divided by VR into 100 for leading load. The only difference from the earlier one, that is like lagging load to leading load, is here. We have here minus, and in the previous case it was plus. So in general, if theta is equal to 0, you don't have to worry about leading load or lagging load, because in that case current is in phase with the voltage. So cos theta will be equal to 1, sin theta will be equal to 0. This will be 0. It will be equal to, this will be 1 IRR divided by VR. Voltage regulation will be this much. If theta is equal to 90 degree lagging, then this is not to be used. Here we have to use a plus. Cos theta is equal to 0, this term goes, and sin theta is equal to 1, this term remains there. It will be IR into X divided by VR. It will be like this. So if theta is equal to 90 degrees leading, cos theta is 0 and sin theta is 1, we have to use this formula. This will be 0, it will be minus X, so it will be minus IR into X divided by VR. These are at different values of power factor, we can get the voltage regulation. So here we can see that voltage regulation is dependent upon the power factor of the load. Now voltage regulation in different conditions. We'll see, I have told you earlier that an ideal transmission line is that which has a 0 voltage regulation but all loads. Here you can see that we can have a voltage regulation of 0 but at a particular load. This will occur only when the power factor is leading. It is because we are getting the voltage regulation formula like this. For leading, for lagging, it is this, because here you can see all the terms are positive. Cos theta for 0 to 90 will be positive, this will also positive, and all the other terms will be positive. This cannot be negative, or this cannot be, this term cannot cancel this term, so it will be always positive. So here for lagging load we cannot have a 0 voltage regulation. For leading load we can have, because this term can compensate this term, because it's a minus term, we can have a 0 voltage regulation. Actually we are exploiting this thing only to have a 0 voltage regulation. So when the power factor is leading, voltage regulation can be positive, negative, or 0 depending upon the theta. From here, if R cos theta is greater than X sin theta, voltage regulation will be positive for leading load as well. If R cos theta is equal to X sin theta, voltage regulation will be 0. If R cos theta is less than X sin theta, voltage regulation will be negative. For leading, we have all the three voltage regulations: positive, negative, 0. For lagging, it will always be positive. So from here, when the voltage regulation is 0, R cos theta should be equal to X sin theta. That means tan theta is equal to R by Z. But this theta is a power factor angle. When we make the impedance triangle of R and this R and X, this will be X, this will be R, this will be Z. So this angle will always be the impedance angle. So but here we get from this relation, this tan theta is equal to R by X. That means this R by X. That means theta comes out to be this, power factor angle comes out to be this. So you can see from here, and the power factor comes out to be X by Z. Power factor will be equal to cos of theta. Cos of theta will be equal to X by Z, that is base by hypotenuse, because base for this angle will be this. So from this triangle, or from this, you can see that this theta Z and theta Z is the impedance angle and theta is a power factor angle. They are related by this, they are the complementary angles. So to have a voltage regulation of 0, power factor angle should be the complementary angle of the impedance angle. You can conclude here, for making the voltage regulation 0, the load power factor angle should be equal to the complementary angle of the impedance angle of the transmission line. So in that case, we can make the this voltage regulation to be equal to 0. Now, maximum voltage regulation. This will occur only the lagging loads. Maximum positive voltage regulation, it will occur only at the lagging loads. So what will be its value? So we'll simply differentiate this term, that is voltage regulation is given by IR by VR, IR this R cos of theta plus X sin of theta. When we differentiate this with respect to theta, so it comes out to be IR by VR, it is same, minus R, because the differentiation of cos theta is minus sin theta, and differentiation of sin theta is cos theta, is equal to 0. From this, R sin theta is equal to X cos of theta, that means tan theta is equal to X by R. tan theta is equal to x by r, which is also equal to theta z. That means this maximum voltage regulation occurs when load power factor angle is equal to the impedance angle of the transmission line. In that case, theta is equal to theta z, and cos theta, that is power factor, is equal to r by z. R is the value of the resistance of the transmission line, and z is the impedance of the transmission line. If they are related to each other by somehow, in that case, max voltage regulation will be maximum. Now, condition for negative maximum voltage regulation, it will occur, as I have told you, only in the leading power factor when r cos theta is less than x sin theta. How much less? And or we can say tan theta is greater than r by x. You can see, you can get this one. You can divide this sin theta by this cos theta, and x will be over here. That means tan theta is greater than this r by x. And this occurs when theta is equal to 90 degree leading. We have already calculated. It comes out to be minus IR x divided by VR. We have already calculated it here. You can see it from here. It is minus IR x divided by VR. So I have from the tabulation I made the tabular comparison of the voltage regulation at different conditions. That is loading conditions. Voltage regulation will be equal to 0 when theta is equal to 90 minus theta z. That means they are the complementary angles, and theta is equal to tan inverse of r by x, and power factor will be leading. It will be maximum when theta is equal to theta z. That means load power factor angle is equal to impedance angle, and it is equal to tan inverse of x by r, and the power factor will be lagging. Voltage regulation will be negative when tan theta is greater than r by x. We have actually taken it from here, and power factor is leading. Negative maximum will be when theta is equal to 90 degree. I should have mentioned over here, theta is equal to 90 degree leading, IR x divided by VR. Please try to mention over here when theta is equal to 90 degree. One more important thing, 0 and maximum voltage regulation coincide when theta is equal to pi by 4. You can see it here. When theta is equal to pi by 4, that is actually this should have been theta z. When theta z is equal to pi by 4, this theta will also be equal to pi by 4. From here, pi by 4 means 45, and this is 45. This comes out to be 45. This also comes out to be 45. That means cos theta will be equal to 0.707. But for a 0 power factor, but for the 0 voltage regulation, power factor should be leading, and it is lagging for the maximum voltage regulation. I hope you understand this. I will stop here. Thank you.